All right. So what we have seen, and that is going to be your biggest difficulty in the beginning, to move away from the time domain, where you think of voltages, AC voltages, as like a sine or a cosine of some sort, and move into the frequency domain, which also in the beginning, at least, we have introduced as a phasor domain, but in reality is the frequency domain. And what happens when you go from the time domain, where you have signals of the, where your source is like a cosine omega t, all right? You go now to a frequency domain where your source is like the phasor of the cosine omega t, which is like the amplitude only. So practically, even if your source is gonna always show like this here on the left, that is gonna be how sources, AC sources in the frequency domain is gonna look like. Whenever you have a source that looks like this, that's a battery, that's DC. And whenever you have a source that looks like this, that's an AC. So that's what that's the kind of the definition, or at least the symbolic representation of DC and AC sources. That's how it's going to be. So now from now on, you will see, contrary to what we had in the previous cases where we had a battery connected in DC, for example, whether you have a DC current or whether you just have charges, you will show like a capacitor, you will show a DC source connected, but now we're going to have AC sources. So you have that here. And all of this here is an intermediate representation. All right, so what you're going to see here, we're not going to see it again, but this is an intermediate representation where we are in the phasor domain, but how I show you the wave here, I show you the wave in the time domain. So to help you move from one domain to another. But the one thing that you have to remember is that in the frequency domain, we don't have time anywhere. What we have in the frequency domain are complex entities, like quantities, like we have a complex voltage, we have a complex current. You don't see time anywhere. You see frequency, which comes here in the beta, all right? But you don't see time. And you have a variation with respect to distance, to space. So space here becomes important. And it shows up the variation in space, which is Z. It's only one dimension, all right? In transmission lines and what we call ideal transmission lines, we call them ideal because we represent them like this. In ideal transmission lines, there is only space variation here and frequency variation. They're both showing up in the exponent. Okay, so we saw that. Beyond that, Kirchhoff's laws, whenever appropriate, will apply, obviously. What that means is that if at the end, your load is a very large, as an infinite resistor, is an open end, that implies that at this point, you have an open end condition, which means that the current at this point is zero. However, it does not mean that the current at this point is going to be zero. This is not DC. There is the current varies along the Z direction. And where does this show? Here. So the fact that you have two terms that sum together, two different terms that sum, that each one of them is a function of z, it shows that in some locations, these two terms will cancel out, and in some other locations, these two terms will sum up. So now we are going to solve problems to see exactly what is happening. And the problems I'm going to solve are the following. So examples. Okay, so first of all, we are going to consider, let me draw one line because we are going to use this over again. So here we have a transmission line. All right, that's how we show them. And then here, this one. And here I indicate the beginning of the line, the end of the line. And what I'm using for this is A prime, B prime. All right, the distance here always for a distance, for the coordinate, one coordinate Z, I'm gonna assume that this is at 0. This is always the placement at the source. And this is at Z equals L, where L is the distance along the line. You can call it D, you can call it L, you can call it whatever. And in fact, so we don't get confused, why do I not call it D here? Because L sometimes is difficult to write it. We all write L in different ways, but D is the same. Okay. Now, what are the other important things that I have to give to this line? There is a set of parameters other than this. There is a set of parameters I have to give you, and I can express this set in two different ways. So I will put it here on the right, and I will use a different color. So parameters here of the line that I need to give you, or whoever asks you to solve the problem needs to give you. The sets can be in two different forms. Either, so set A, I'm not going to give you both. I will give you either one or the other. So either I'm going to give you L and C in unit lengths, so for example, and I will give you an example later, lengths, or B, I will give you Z naught and beta. And I will assume at this point also that these are ideal and lossless lines. Okay, that's important. So B, I will give you Z naught or beta. Now, for those of you who want to have the notes ahead of time, I'm working on these examples, but the notes you have are the notes that I have already incorporated in your documents. So instead of adding one more similar document, you have those you can write down, and then I will add those examples that I'm giving. Why is it only one group or another? All right, why is it only one or another? Because one group gives you the other. So for example, if I give you L and C, we know, so we know here, what? That Z naught is square root of L over C. And we know that beta is omega square root of LC. So these two, one can give you the other. So either I'm going to give you L and C and of course the frequency. The frequency is always very important. Or I will give you Z naught, beta, and the frequency. The frequency is an independent parameter. It's a fundamental parameter, and you need to have it. You cannot derive the frequency unless I give you, let me see. Okay, frequency is fundamental, comes from the source. All right, so having that in mind, this one here, usually what I will give you in most of the problems, it will be Z naught and beta. All right, practically I will give you, I give you the two, and then if I give you beta and then of course the frequency, and I may give you the frequency in F or omega, and if I give you beta, then it's gonna be in, if I give you beta, it's gonna be in radians per, second. So anyway, so that's what we have. Also, another parameter that we are defining here, which is important, is that beta is, let me see, beta, omega, excuse me. Let me write it here before I go. There is a formula that beta is 2 pi over lambda, but let me remind you the following. Omega is 2 pi f. All right, and f is what? How is f and lambda related? F, lambda is the wavelength. F times lambda is c. But here, the wave goes with a different velocity. So, or it can go with the velocity of light. So a lot of times I will give you F, I can give you lambda. So let's assume that it's C over lambda. All right. So practically, I'm giving you here the fundamental formulas that I can give you. So a lot of times I can give you frequency. When I give you frequency, I have already set the lambda, the wavelength, where lambda is the wavelength. Do you remember these formulas from previous, from circuits or from whatever in the classes that we had so far? The lambda, at least in physics, that F times lambda is C, which is the velocity of light in the medium. Here there are ideal transmission lines. Obviously the velocity of light will assume that it's the same, like in free space. Okay, so these are your parameters. All right, now we go here, we start. In the beginning, in many of the problems, I will show you in either directly the source, and then I will say, this is my V source phasor form. So I'm gonna give you just the amplitude. All right. And then I will give you a load. The load is here. These are the fundamental problems that we are gonna solve today, load. And I will indicate the load like this. Now, what you need to remember is that the generic solution in this problem is always the same. And here is what we are using to define it. First of all, I will start with the following. We always know that V, which is the voltage wave, as we call it, V of Z, that goes in the line, and this is the current. We always show it on one of the lines. There is always a return current on the other. There is always a current that goes like this underneath, but we are not going to show it to save space. So we show only the current here. And we know by now that V of Z has two components. I will show it here. I will write it clearly so you see them. V of Z plus plus V of Z minus. This is called the incident wave. And that's the reflected. And then we have I of Z equals, I want you these formulas I want you to remember them by heart. Not because I will take the books away, but because you at least are the fundamentals. You need to remember the fundamentals, and they are not difficult. This one plus I minus Z also is called the incident and the reflected, okay? And then we have also, we can represent each one of them in the following way. So this goes here, and I write it as V of Z equals V naught plus e to the minus j beta Z plus V naught minus e to the j beta Z. And again, this is incident and reflected. All right, so maybe I need to turn this one. Incident and reflected, so you remember all of them. On the left are the incident, on the right are the reflected. And then also we write I of Z to be equal to V naught plus over Z naught e to the minus j beta Z minus V naught minus over Z naught, remember that, e to the j beta Z. Okay. Now, let me put also this in red so you remember it. The sign here is negative and here is positive. Now, there is another thing that we are going to introduce, two other parameters very important, which we are going to use in this problem. So from here, we introduce two more parameters. The reflection coefficient, very important, we call it reflection coefficient. The reflection coefficient is a function of Z, gamma of Z, and it represents the ratio of the reflected voltage over the incident voltage. And because the reflected voltage, which is this one, and the incident voltage, which is this one, are functions of Z, that's why gamma of Z is also a function of Z. All right? And because of the previous formulas that of V of Z, the incident and reflected, so I can write here that this is V naught minus over V naught plus e to the minus zeta 2 beta Z. Remember the 2 component here. I will put it in red. And 2 beta Z, let me see, red. I want you to remember the 2 because many students forget that. 2 comes from the fact that and it's, I said, so it's plus also. 2 comes from the fact that we divide this one by this one. All right, and that's why we have 2 beta Z there. And then we have another important parameter we introduce, which is the input impedance. And the input impedance is also a function of Z. And how do we define it? We define it as the voltage at Z divided by the current at Z. It's the total voltage divided by the total current. And this is equal. There is a formula which you can derive, but I would like we will be able to derive this if you substitute. I will show you we're not going to do all the derivation, it's very easy, but I will do this here for you, just to show you how we derive this formula that I will write. And then you have V naught plus of Z naught e to the minus J beta Z minus V naught minus over Z naught e to the J beta Z. And finally, this one, I'm going to add a page. This one is giving you the following: Z input at any point Z equals to Z naught ZL, which is your load, and I will explain that, plus J Z naught tangent of beta Z plus Z naught divided by Z naught plus J ZL tangent of beta Z. Okay, so this is a very important formula. Then you can derive from the above, where now, put it there, Ed, where now ZL is given by V at Z equals D divided by I at Z equals D. That's the load. That is the condition for the load at the end of the line, because at Z or at D, at Z equals D, you have here plus and minus V of D, and then you have here I of D. So practically by incorporating all of this, let me also reduce the size here so we have space. So that becomes smaller and this becomes smaller. So these are the fundamental formulas. With these ones, you can solve any problem. And so now we're starting the examples, and we're going to solve examples from that point on. Any questions up to now? This is,
Yes.
yes,
Could I?
yes.
I'm sorry. You go.
Go ahead.
Oh, okay.
I cannot hear you very well, so
Um.
we're going to speak up.
So far, are we just assuming the wires are just lossless?
Yes, here. You see that?
Oh yeah.
All right. Now let's assume that we take this now and we're going to use different loads. So let me take and copy this so I don't draw it again. Paste.
Professor,
Yes,
I just wonder, can you scroll up? I see like we have a IC equal to like I plus with I positive plus with I negative, but on the second equation, I see it have a minus sign.
yes,
So yeah,
because there is an important relationship you need to remember. So Z naught, the characteristic impedance of the line, you saw that here. I will write the relationship here also. There is one more relationship you need to remember, that Z naught equals V naught plus divided by I naught plus, but Z naught is equal to minus V naught minus divided by I naught minus.
oh, I see.
There is a minus sign there.
Yeah, yeah, thank you, Professor.
Oh yeah. All right, so now let's assume number one example here. So we wrote just the formulas before. A, assume that ZL equals 0. What is that? That's a short. assume that at Z equals D, we have a short circuit. So what this is gonna do, let me first of all erase this one. I need space, obviously. So we'll assume that this one is open. Is short, excuse me, short. So I will put a short here. All right, first of all, if we have a short, we can find the input impedance at any point. So let me here give some, so let me call this 1, 2. All right. So from 1, we have that the reflection coefficient at any point on the line will be V naught minus, I mean, it's gonna always be, maybe, let's go before there, before we write those. What are the conditions on a short? So conditions at load. When we have a short, what happens to the voltage? When we have a short circuit, when we have a short circuit at the end of the line, then the voltage is 0. That still applies. The voltage between B and B prime, because this is the voltage between B and B prime. All right, the voltage at the end of the line is 0. That's extremely important to remember. Okay, because the voltage is 0, look at that. That means at D, I can then write next to it, because of that condition that I have, V naught plus at E minus J Z D plus V naught minus at T Z, excuse me, exponential J Z D equals 0. So that gives me a relationship between V naught plus and V naught minus. So I have that V naught minus, I can write, is V naught minus is minus B naught plus E to the minus J to Z D. So that's what these two are giving me. That also means that at my source, right at Z equals 0, and that is always the case. But if I put Z, so here at any point on the line, that's what I wanted to show you here. What does that say? That says that your voltage may be 0 at the end, but it's not 0 everywhere else. So for example, if I write now my voltage for this, V of Z will be V0 plus E to the minus J to, beta Z plus V0 minus E to the J beta Z. And now I replace my V naught minus with a V naught plus, and I have V naught plus E to the minus J beta Z minus V naught plus E to the J beta Z E to the minus J 2 beta D. And practically here, I can write this as V0 plus E to the minus J beta Z. And inside I have 1 minus V naught plus, minus, I got the V naught plus out, minus E to the J2 beta Z minus D. All right? Did you see that, how I write it? Let me write it clearly here. Z minus D.
Professor,
Yes.
when you were first defining V naught minus in terms of negative V naught plus, did you mean to write a beta in the exponent of a Z?
Yes, thank you. Thank you. Thank you. So that tells you that when this expression tells you, gives you here, that when you can find from this one, that when Z becomes equal to D, then E to the J2 beta Z minus D becomes E to the J0, which is 1. And then so 1 minus 1 gives you 0. So that implies from the above that V at Z equals D is 0, which in fact satisfies our condition. So why is this important here as an expression? Because what is different between circuits, and that's what I wanted to bring to your attention. In circuits where you don't have distances, physical distances, when your voltage is 0 at one point in your circuit, and then you just have a straight line that connects the other points, I mean the source to this point, then if it's 0 there, it's 0 everywhere in circuits, all right, unless you have some other circuits involved. But here, if you have just a line and you have a 0 at one point on the voltage, it does not mean that the voltage is 0 everywhere else. The voltage here is not a real number. The voltage in the frequency domain is a complex number, as you can see here from the red. The voltage here, which is different from circuits. Here we have complex numbers, and they change with the distance. That is the fundamental difference from circuits. So when a voltage is 0 someplace, it's not necessarily 0 any other place. So keep that in mind. There is also the same way you can, from the voltage, develop expressions for the current. But there is, I'm not going to do that for this case, because let's assume that somebody wants us to find here. Assume that I did not write what we wanted to find. So I'm going to write it here. Find input impedance at the source. Find input impedance at A prime. So that was the problem here. Okay. Nice. Okay. So now let's try to find the input impedance. Next. I'm not going to rewrite any formulas. I will remember what I have in mind, what we derived before. We found that Z input at any point Z is equal to Z naught ZL plus J Z naught tangent of beta D, beta Z rather, for the, since it's at any point Z, and then is Z naught plus J ZL tangent of beta Z. All right, now, what do we have for this problem? From here, since I'll put in parentheses, we have that ZL is 0, and we have that Z equals D. So we have an open circuit at this distance from the source. So then Z input at any point Z, I will put ZL equals 0, so it's going to give me Z naught, J, Z naught again, tangent of beta Z divided by Z naught. So this and this goes. So practically we have that Z input at Z, at any point Z, is J Z naught tangent of beta Z. Okay, now look at that. And then tell me what you observe. What happens when your line is short-circuited at the end? What happens to the input impedance everywhere on the line? What do you observe from here? What is this missing? Or what is it characteristic about this number, this expression?
It only has the imaginary part.
Yes, yes. So what we see here is that Z input is reactive everywhere. So Z input is reactive. What reactive means exactly, it has only the imaginary part. It can be either positive or it can be negative depending on the tangent. Now, one more thing. From now on, and I will say it here, I will put it also with green. From now on, to simplify things, we are going to normalize impedances as long we have the same characteristic impedance on lines. So practically, to simplify my expressions, I will normalize the impedance, and we'll show it like that, which is going to be Z input at any point divided by the characteristic impedance. You can normalize only if you have the same characteristic impedance in all of your circuit, or you normalize only in the place where you have the same characteristic impedance. Okay, so now we only have that, obviously, which means that there are two things that implies for the general case. Z input normalized is going to be ZL normalized plus J tangent of beta Z, and then is going to be 1 plus J ZL tangent of beta Z, which means that you have simplified your expressions. And for the case of a shorted line, when the line is shorted, then your Z input normalized becomes J tangent beta Z. All right? So now let's see how that is going to change along the length of the line. So let me here try to take this expression and try to see how it varies. So find how it varies as a function of Z. Okay, so here I'm doing the following. Right, maybe I need 1 second. I need to do this well because we have a little more complexity. All right. There. Okay, how are we gonna measure Z? That's another thing that I wanna tell you. Do you see here that we always have beta Z? So beta Z, let me move a little bit this lower. Beta Z here is nothing else. We can write beta as 2 pi lambda. Okay, beta Z. Lambda, therefore, is how we define beta here. And then it's 2 pi over lambda times Z, which means from here that I can rewrite this beta Z as 2 pi and then Z over lambda. So practically, I normalize now Z as a function of lambda. And that's where we are going to stay. In fact, from now on, you need to think of Z as a function of the wavelength. So that is extremely important. And let me see. I will put this in red. Oops. So you remember it. As a function of lambda. So always when you plot Z, you're going to plot it, or you're going to think of this as a function of lambda. Very few times in the beginning, maybe I'll give you Z in physical length dimensions. And then you will always try to find what function of lambda is going to be, because if you don't, if I give you the frequency, obviously, and if I give you Z in physical dimensions and you have the frequency, you can find lambda. And so from there you can find Z. But the moment you have normalized Z in that form, so then in that case, you can call that as normalized Z, then the only thing that you have to do is your beta then becomes 2 pi Z normalized, but now the normalization is with respect to lambda. And then we're not going to solve the bar anymore from that point on. We will always assume that it's normalized. Okay, so now let's look at Z as normalized function of lambda. So what we're going to do, let's assume that this is, of course, it's a function, is a cosine sine function tangent. So it repeats, all right, every 2 pi. So practically we are going to have here Z in terms of lambda. So we're going to have lambda over 2. We are going to have lambda rather over 4. Let's do this a little more. So it's going to be lambda over 4, 3, 4, lambda over 2, then 3 lambda over 4, and then lambda. And then you can continue the same way. So now let me plot it. I'm going to plot it this one, different color. All right, so here, what is tangent of 2 pi? And then since it's normalized, it's going to be, so let me write here. So for this one, beta Z is going to be 2 pi over 4. So practically it's going to be pi over 2. Pi over 2. How much is the tangent and pi over 2?
Infinity.
Infinity, yeah. So it goes like that. All right. And then what happens below it? Let me move this a little too. There. So what happens below it when it goes just above that?
It approaches negative infinity.
Exactly, comes from here. Oops. And then it goes to 0. And then the same thing here. So it goes like, in fact, let me see, it goes like this and like this. Okay. And then the same thing here. Let me see this one. It's not a good thing. Let me just do it here. It does not go under. It goes tangential to 0, slowly rather, like that. And then again, it repeats the same thing. So it goes like this, like that. That is how the impedance goes on the line. So since tangent goes like that, and my impedance has been this for a shorted end of the line, that means that at z equals 0, my impedance is going to be 0, which is like the source. All right. So then it's going to start going up, and the lambda over 4 is going to be, let me see, at z equals 0, right? Let me see, tangent beta z from the z, yes. Well, let me see, this one we measured z from the source. So I'm sorry, I have to make a beta z minus d. So here, I'm sorry, I will have to make a change because I always, in my previous classes, we had a different book. So let me show you here what I have. A correction I'm gonna make. Correction here. Z minus D. All right, so it's the distance from the load. Oops. Z minus D. Okay. Z minus D. And then if we call Z minus D to be Z prime, so that's the distance from the load. Then this is about Z prime here. All right, so you remember this one, that it's the distance from the load, not the way we have it in our coordinate system, because it was this one. All right, so here is Z minus D, Z minus D, but this is the distance from the load. Okay, so in fact, it will be also to be right with a sign. Let me be correct with the sign 1 second. It has to be positive here. So it's gonna be D minus Z, D minus Z. I wanna be careful with the coordinate system we have. So because Z is gonna be always less than, so here, let me change that, D minus Z. D minus Z. So if you remember that Z prime is always the distance from the load, so this is Z prime, then this is Z prime. I will put it there so you remember it, Z prime, and this is Z prime, okay? This is for any Z here, all right, for any Z normalized. So this is Z prime normalized. This is the distance from the load. When we are right at the load, at this point, this is the impedance. The distance is from the load. When we are right at the load, all right, where Z prime equals 0, then you have a short, you see that. But when I move away from the load, so let me just show you one, let me do some graphs here at the page. Okay, here. Okay, I will add a page here. Now, when this is our line, let me put our line here. Copy. Paste. And I need to cut this one. Okay, that's our line. See that? So this is the distance. This is the coordinate system, but the distance from the load, I have defined it like this. Like this. Okay, this is my Z prime. So when I am on the load, it's right here. That's at the load, at load. So it starts at 0. And then as I move from the load, I come to the point which is a quarter of a wavelength away, and then I see an infinite impedance. So what happens here? It's an open. So it starts as a short, then in a quarter of a wavelength becomes an open. In another quarter of a wavelength, which is lambda over 2, it becomes another short. So here is another short. And then another quarter of a wavelength, and is another open. And so on. So that's what you see on a line like that. As you move away from your load, the impedance changes, which is very different and characteristic of transmission lines. All right, so now you saw that we're gonna start also solve problems with an open, and then we're gonna go to different types of things, but it's gonna be always the same functions, the same parameters that you see here, and we are gonna use them over and over again for different loads. So with that, we're gonna keep going. And on Wednesday, when we do also one more example, I'm gonna also introduce the Smith chart. So you can see the same things visually on something we're gonna use is very useful for circuit design, high frequency circuit design. Any questions?
I guess I have a hypothetical situation. Well, not hypothetical, but like a more realistic
Yes.
situation with power lines. So yeah, you know what a power line looks like. It's a big cable with a bunch of twisted wires that
Yes.
go through it. So being that it's a bunch of kind of twisted wires,
Yes.
in a way it kind of looks like a stretched out solenoid. So would you still be able to assume that
Yes.
in a real
Because-
case that just
yes.
solid, or can you?
Yes, because the twisted wires, usually there are, all right, in reality, there are a multi-conductor lines. So you have one, the twisted wires, are you looking at an Ethernet cable? That's where there
Well,
are.
it could be an Ethernet cable, but I was thinking just like the large power lines, how they're
The large
like
power line.
that.
Usually you always have you have lines like that braided, when we call them, they're not solenoid, but they're braided. And they do the braiding just so they can stay together, right? Obviously, it's for practical reasons, but each line is one transmission line. Each line, all of the lines will share a conductor, or all of the lines, each line, depending. In the Ethernet, they will share a conductor. They will like have their own conductor that eventually is connected. All the conductors are connected at some point in the beginning. In power lines, I think, I don't know whether, I have not seen braided in power lines to tell you whether they have their own conductors or they share the same. But they will be kept in a distance. When they share the same conductor, the design is a little more complex. But all of these are two wired transmission lines, each one of them.
Okay, and they just assume that the insulation around each
Yeah.
line is enough to prevent from
Yes.
inductance from affecting. Okay.
Yes,
Okay,
and
that's-
from short circuits and all of these kinds of things. Correct.
Okay, that's all I had. Thank you.
Sure. Any other questions? Okay, so this one, I'm gonna put it up. I'm gonna do it this right now, email it to myself. And I'm gonna remove this and remove everything else. And I will put it up. So email notes to me. Not wrong. And I will put it up for you. But this is how we're going to solve problems from now on. It's just that every time we solve a problem, we're going to go a little faster and a little faster. We are not going to write all of this extensively, this kind of thing. All right, we're going to skip some things because they will be identical. Yes.
Dr. Katai.
Yes.
So for the future problems, do we always assume the wires or the lines are lossless?
Yes, and
if not
yes,
specified?
for all of this class, from now on, we'll assume that the wires are lossless.
Like even if like it says the wires like a copper lead, like the homework,
Yes,
a copper leads.
yes,
Like of the
yes,
diode.
lossless, everything.
Okay. Well, that simplifies a lot.
Of course, because no, we're not gonna do with
Thanks.
lossy. It's for another class.
Okay, yeah, because I was trying to like solve for the alpha part.
No,
It's 9 o'clock.
That was
No.
difficult.
yes, no, we're not gonna do that.
Okay, cool. Thank you.
You're welcome. All right, so I will see you office hours today for any questions. Take care.